Hello friends, in today's lecture we are going to discuss about the reactions in case of 6-member ring system, and in that case in last lecture we already seen about alpha haloketone effect, and in alpha haloketone effect we already seen when the substituent is present on adjacent to the carbonyl group present in the 6-member ring system is present preferentially at axial position and not in equatorial position. When that substituent is methyl and somewhat bulkier than that, okay, and this condition is only favorable for in some cases where there is no presence of more than one substituent on the more than two substituents on the 6-member ring system. Okay, so here we take one example with the alpha haloketone effect. Here we take one example, one for addition of phenyl magnesium bromide. So first we try to write here or draw here structure of here. First I would like to draw here acetyl cyclohexene. So this is the simple structure of acetyl cyclohexene, and when that planar conformation is converted into the chair conformation, at that time we have this type of two. Here these two carbon atoms are Sp2 hybridized, and all other 4 carbon atoms are Sp3 hybridized, so that here the geometry of 6-membered ring is somewhat distorted, and in that case 4 adjacent carbon atoms are in one plane due to the presence of double bond and Sp2 hybridized carbon atom, so that here we don't write this bond exactly axial or equatorial, this is middle of that, and here I write phenyl. Okay, so here first we write phenyl at equatorial position and somewhat like that. So here is no presence of phenyl in the reactant. Why? Because we can add as a nucleophile in the double bond. Okay, so here we get a last product, or first we add here phenyl magnesium bromide. One for addition of phenyl magnesium bromide into the acetyl cyclohexene. Okay, and what is the question? Question is the enol which is then upon acidification ketonizes in such a way that the proton approaches equatorially. Okay, so how that proton will approach in equatorial direction? Okay, first this pH minus, okay, which acts as a nucleophile, and that nucleophile will attack on this position. At that time this double bond will move here, which can form enol. Okay, now what is the product of this starting material? So here we have phenyl. Here we write here we have double bond, here oxygen, we write here MgBr, and here this is methyl group. Okay, now acidification is carried out, H plus, and when this O minus will convert into the carbonyl group, and when that double bonded electrons will given to the H plus ion, at that time this H plus ion approaches to this carbon atom from equatorial side. Okay, so we get here the next step having this is carbonyl and this one is methyl group, and here that proton is present on the equatorial position. Okay, if that proton is present on the equatorial position, at that time we write here next, if the bromination is carried out, but here we write before that, suppose here we use base, and that base will first pick up this proton, and here is formation of enol. Okay, here first we get enol, okay, here we have phenyl ring at equatorial position, and after that we get here bromination. In this step we bromination is carried out. This bromine also approaches from equatorial side, and here we get a final product, and that final product is suppose here this is carbonyl, here this is bromine, and here this is phenyl ring. Okay, so this product we get in such cases where the sp2 hybridized carbon atom is present. At that time such a type of product must be get. Okay, in the next case, suppose that reaction is carried out in same manner, but the proton approaches from the opposite side, means what, the axial side is preferentially add. So what is the product? Okay, the same thing is possible in second step, and here that proton approaches from axial side, and here we try to write the product getting from this. Here this is phenyl group. Now the acetyl group which can be present at the equatorial position, and here this proton is present. Okay, proton present in axial position, so that here we write next step, and first we use here base which can abstract this proton, and here we get double bond or we get enol. Okay, but in this case here the base doesn't abstract this proton. Why? Because that proton is present on the axial position. Okay, and here there is formation of double bond on the cyclohexyl ring system, or the carbon atom which is present on the cyclohexyl ring, so that base will abstract the proton from the methyl group, proton from methyl which is present on the acetyl group. Okay, and not the proton abstracted on cyclohexyl ring, so that here we get different product. We get different product. Here we write pH. Here this is proton. Now here we get we write here like this, and here enolization O minus. Here we get double bond, and we write CH2. Okay, now in next step, bromination. Bromination is carried out. Okay, this enol can transform into the ketone or carbonyl, and this double bond will attack on bromine. Okay, and now we get here your last product, which is phenyl ring. Here this is proton, this is carbonyl, this is CH2, and this is bromine. So here we get 1 bromo, 1 acetyl, 2 phenyl cyclohexane is the product, and in this case also we get 1 bromo, 1 acetyl, and in second case bromoacetyl. Okay, bromoacetyl 2 phenyl cyclohexane is the product. So how that two products we get? Okay, and for the explanation of that, when the equatorial hydrogen is present in compound first product, at that time the geometry of that two eliminating groups and the presence of double bond is, here we get this proton and phenyl group, both are cis to each other, and in first case both the proton and phenyl both are trans to each other, in this case bulk accommodated at the equatorial side, so that it doesn't interfere in the stability of the compound, so that this compound is somewhat more stable than that of earlier. Okay, and in next case we take another example regarding monosubstituted and disubstituted compounds. Suppose sterically hindered compounds. Here we take one example in monosubstituted cyclohexane. In monosubstituted cyclohexane, here one question is always asked in examination. So we take that which is not concerned with the alpha haloketone rule, so that you don't confuse. But here we take that example. Suppose question is which conformation of 1,2,2,6 pentamethyl 4 hydroxy-4-phenylpiperidine. First we try to write here what is the name of that compound. 1,2,2,6,6 pentamethyl 4-hydroxy-4-phenyl piperidine, 4-phenylpiperidine. Okay, so this is the name of our compound, and here the question is asked. Which question? Which conformation is more stable? So here we have one question, okay, and in this case first you try to convert this name into the planar conformation, and here suppose we have this is 6-member ring, and in this case here suppose this is piperidine contain nitrogen, okay, 4-phenylpiperidine, 4-hydroxy-4-phenylpiperidine. Okay, so here we write 1-methyl. Suppose this is 1, 2, 3, 4, 5 and 6. Now 1-methyl, suppose this is 1-methyl, 2-methyl, 2-methyl, 6-methyl, 6-methyl. These are the pentamethyl, 4-hydroxy-4-phenyl. Suppose this is 4-hydroxy and this is 4-phenyl. Means what? Two substituents are present on the 4th position. Okay, and now we convert this structure into the chair conformation, and whichever is more stable, either that is chair or that is boat conformation. Okay, first we try to convert that into the chair conformation. So here my structure is look like this. Suppose here this is first carbon atom and here 1-methyl is present on that nitrogen. Then these are 2nd and 6th position, methyl, both methyls are present. So these are the pentamethyl, and here 4, suppose we write here phenyl and here we write hydroxyl. And why I would like to represent that hydroxyl group on axial position, and why not at equatorial? So here we compute the size of the substituent present on the same carbon atom. At that time phenyl group is somewhat bulkier as compared to hydroxyl group, so that we put that hydroxyl at axial and phenyl at equatorial position. Okay, now this structure is somewhat stable, but in such cases having the presence of heteroatom on 4th position and 1st position, at that time there is somewhat correlation between the stability, okay, in chair and boat conformation. So that here we try to convert that structure into the boat conformation. At that time we have seen the stability is more in the boat conformation. Suppose this is nitrogen Okay, and here we try to put hydroxyl group, and now here you see there is a linkage between nitrogen and hydrogen is possible, and here these are the methyl, here also methyl, here is methyl, and here also methyl. These are the pentamethyl, and here this is phenyl ring. Okay, so this is the most stable conformation. Why? That's conformation which contain there is formation of hydrogen bond. Why? Because due to presence of this hydrogen and nitrogen, both are very close to each other, and so that they will form hydrogen bond. So this both conformation will get converted into the stable conformation than chair conformation. Okay, and this conformation is look like, suppose this is our boat and this is the loop, which is also a 6-membered ring. Okay, here this is also a 6-membered ring system, 1 2 3 4 5 and 6, so that here we get a bicyclic ring system, and in that bicyclic ring system 6-membered ring is more stable, so that both conformation is more stable. Here we write more stable, and here the chair conformation is less stable. So you remember, students, the hydrogen bond formation due to the presence of heteroatom at the first carbon atom is replaced by nitrogen, so that here formation of hydrogen bond, and due to formation of hydrogen bond, this conformation, both conformation is more stable than that of chair conformation. Okay,